Hello everybody, welcome to chemistry class. Today's chemistry class, the learning objective is Hsab applications. Previously, I've discussed about the Pearson theory, Hsab theory. So the stability of the complex depends on the type of the ligand and the metal ion. So for the formation of a stable complex, the type of the metal ion and the ligand must be known. So type A or class A metal ions, their characteristics. Type B and class B metal ions and their characteristics. And type A or class A ligands and their characteristics. Type B or class B ligands and their characteristics. All these were explained, and the Pearson theory, basing on the Pearson theory, we are having the HSAB applications. So, to predict the stability of the complex or coordinate complex formed between the acids, that is metal ions, and bases, that is the ligands, Pearson suggested a rule, that is Pearson HSAB principle. So this theory is quantitative concept. It was introduced in 1960 by Ralph Pearson to explain the stability of the metal complexes. It also explained the mechanism of the reactions. The stability of the complex or the coordinate compound formed between the acids and metal ions is suggested using this principle. According to this principle, hard acid prefer to form bond with hard base. Soft acid prefers to form bond with soft bases. And different types are hard Lewis acids, soft Lewis acids, hard Lewis bases, soft Lewis bases, and borderline. See, in the hard Lewis acids, these are characterized by small ionic gradient, high positive charge, strongly solvated ions, and empty orbitals in the valence shell. These also have high energy, lowest unoccupied molecular orbitals. These are called as the hard Lewis acids. It is one category. Now, the second category, the second class of the compounds are where I'm telling you the class B metal ions. These are the soft Lewis acids. In the printing, it's almost this typing has gone wrong, it's the same, both of them. But the soft Lewis acids are, these are characterized by large size. Here it's given small ionic gradient, but large ionic gradient, low positive charge. And these are less strongly solvated. These are filled orbitals in the valence shell with lowest energy unoccupied molecular orbitals. Low energy, lowest occupied molecular orbitals. Coming to the hard Lewis bases, these are characterized by small ionic gradient, strongly solvated, highly electronegative. These are weakly polarizable and with high energy, highest occupied molecular orbitals. Coming to the last category, that is type B ligands or class B ligands. So hard Lewis acids are type A or class A metal ions. Soft Lewis acids are type B or class B metal ions. Coming to the hard Lewis bases, type A or class A ligands. And soft Lewis bases are type B or class B ligands. These are characterized by large ionic gradient, intermediate electronegativity, highly polarizable, and with low energy homos. Highest occupied molecular orbitals. Coming to the borderline, Lewis acids and bases have intermediate properties between the hard and the soft. It can be acid or a base. As I've explained, the hard soft acid base concept, Hard acids prefer binding to the hard base, and ionic complexes are formed. Let us see the visibility. Whereas soft acids prefer binding to the soft base to give covalent complexes. This is referred as hard-soft interaction principle. HSIP. The larger electronegativity difference between hard acids and hard bases give rise to strong ionic interactions. The electronegativities of the soft acids and soft bases are almost same, and hence they have less ionic interactions. The interactions between these two are covalent. So for the soft acid and soft base, SASB, the interaction is covalent. Interactions between hard acid, soft base, or soft acid and hard base are polar covalent. See here, the one is hard and the other one is soft, or vice versa, soft and hard. So these are polar covalent and tend to be more reactive and less stable. So the polar covalently compound they readily form either ionic or more covalent compounds. So these are not allowed to react. Coming to the periodic table, you can see here the topper ones. So hydrogen, lithium, sodium, potassium, beryllium, magnesium, calcium. These are hard acids, small in size, highly positive. Bottom ones, sodium, cesium. These are less positive and these are large in size and these are soft acids. Now coming to this one, even rhenium, osmium, platinum, iridium, gold, mercury are the soft acids. And coming to the borderline, they have intermediate between the hard and soft acids. And coming to the bases, you can see on the left side of the periodic table, here the ones which are red line. These are hard bases. These are negatively charged, highly electronegative in nature. These are highly electronegative in nature. These are small in size. Okay. And these, along with their small in size, is electronegative nature and non-negative nature. So these are hard bases. And coming bottom, you can see these are the soft bases, large in size. These are large in size and they have less positive charge and form soft bases. And here the violet line ones are the borderline. Here these are the borderline bases. So they have intermediate properties between hard acid and soft base. Yeah, before going to the application part, let me give the key characters of the compounds. Key characters of these compounds. Hard acids. The key characters are these hard acids are low in polarizability, high positive charge, and their size is small. You cannot easily oxidize. As polarizability is low, oxidizability is also low. Coming to the hard bases, these hard bases have low polarizability. Just like the hard acids, even hard bases are low in polarizability. They spread the donor orbital. They have high electronegativity. Just these are having acids are having high positive character. These are having high electronegative character, and these are not easily oxidized. Just same characters, but there it is positive for acids and bases it is negative. And coming to the soft acid and soft bases, key characters. The soft acids are quite opposite to that of hard acids. Soft acids are high in polarizability. Due to the large size, their polarizability is more. Oxidizing power is also more. These have low positive charge. Now coming to the soft bases, even the soft acid and soft base almost the same characters, but for the acids it is positive nature and for bases it is negative nature. Coming to the soft bases, their high polarizability, the diffusing donor orbital, low electronegativity, and they are easily oxidizable. As we have discussed about this principle, before going to applications, HSAV concept tells that hard acid prefers binding with the hard base. Here, blue and these both prefer each other. So hard acid with hard base. And therefore ionic complexes are found which are stable. Whereas soft acid combines with the soft base. So soft acid combines with soft base. And this preference gives to the covalent complexes. It is sometimes referred as hard-soft interaction, HSIP. Now, let us see about the applications of HSIP principle. In hydrogen bonding, the strong hydrogen bond is possible in case of water, ammonia, hydrogen fluoride. Since the donor atom fluorine, oxygen, nitrogen are hard Lewis bases, see, strong hydrogen bond is possible in case of H2, yeah, the universal cell, and even with respect to NH3, and even with HF. See, hydrogen is the hard acid, oxygen is the hard base. Similarly, nitrogen, hard base, and nitrogen is the hard base and hydrogen the hard acid. Similarly, hydrogen here in HF is the hard acid and fluorine is the base. Now, fluorine, oxygen, nitrogen are the hard bases as I've told you. And interaction with partially positive charged hydrogen is a hard acid. That's stronger. Therefore, hard and hard gives to the stable compounds. Here, our principle is getting applied. Linkage of the ambidentate ligands to the metal atoms. Ambidentate ligand SCN minus can bind either SN or NN. Here, isocyanide bond. This is ambidentate, can bind on two sides, from the sulfur side or from the nitrogen side. So the bonding mode can be determined by HSAB principle. It bonds through sulfur atom, that is soft base. And when bonded to the platinum, a soft acid. However, it bonds to the nitrogen, hard base. And it can be linked to the chromium, that is hard acid. So if it is chromium, hard base, this nitrogen is hard base. Similarly, sulfur is soft base. And the bonding is possible sulfur with the soft acid, that is platinum. Similarly, nitrogen can bond with the nitrogen is hard. Similarly, even chromium can bond with the hard acid. So sulfur is the soft base. It binds with the soft acid platinum. Nitrogen, coming to the nitrogen, it is the hard base and it binds with the hard acid, that is chromium plus 3. Now, site preference in organic reactions. Site preference in the organic reactions. RCOX is the hard acid and reacts with nitrogen end of SCN ion to form an acyl iso acyl thiocyanate. RCOX is a hard acid. It reacts with the nitrogen end of thiocyanate. It forms the acyl isocyanate. You can see the reaction CH3COX. This is RCOX example. Acetyl chloride. In place of X, you can take any of the hydrogen. Acetyl chloride. It bonds with the SCN and nitrogen gets bonded. See, the X is the X, RCOX. It is the hard acid. And SCN, the nitrogen, is the hard base. So therefore, it binds from the side. Though it is having S site and N site, the N will come in one. Therefore, the compound which is formed is stable. Whereas softer methyl group bonds with the sulfur. Softer methyl group bonds to the sulfur and forms methyl cyanide. C will bond to S. Okay, if it is acetyl chloride, then if it is acetyl chloride, this oxygen, whatever is this oxygen, it binds, it is the hard acid. It binds with the nitrogen, hard base. So therefore, the stability is more. And for the methyl group, the carbon is softer. It bonds to the soft sulfur, soft base, and forms methyl thiocyanate. So therefore, even this is a stable complex. Now, let us go for the next application. Nucleophilic addition of alpha beta unsaturated carbonyl compounds. The alpha beta unsaturated carbonyl compounds have two types of carbon electrophilic centers. Alpha beta unsaturated carbonyl compounds, there are two types of carbon electrophilic centers. Carbonyl carbon, hard electrophile center, and beta carbon, soft electrophilic center. Here you're having alpha beta unsaturated carbonyl compound. Alpha beta unsaturated carbonyl compound. Here, this carbon, carbonyl carbon, this carbonyl carbon is hard nucleophilic center. So carbonyl carbon, hard electrophilic center. And similarly, the beta carbon is a soft electrophilic center. Here, this is the soft electrophilic center. Now, this hard nucleophilic center and soft electrophilic center. These two, the hard nucleophilic like Grignard reagent attack at carbonyl carbon. Hard nucleophiles like Grignard reagent attack at the carbonyl carbon, that is hard electrophile. Here you can see this carbonyl carbon is hard electrophile. It reacts with hard nucleophile like Grignard reagent and results in 1,2 nucleophilic addition to form the carbonyl group and to form the addition to the carbonyl. 1,2 nucleophilic addition takes place. Now, on hydrolysis, we get the hydroxide. Now, whereas soft nucleophile like lithium, organocuprates, thiols, all these attract the beta carbon, soft nucleophile results. So the beta carbon, it is the soft nucleophile. Beta carbon, it is the soft, beta carbon, the soft electrophilic center. So their soft nucleophile will occur. This is the soft electrophilic center. So soft nucleophile will come and attach here. And similarly in the Grignard reagent, this is hard electrophile. So hard nucleophile will come and attach. Okay. For the soft electrophile, soft nucleophile attaches. For the hard electrophile, hard nucleophile will attach, and thereby the nucleophilic addition of the alpha beta unsaturated carbonyl compounds will take place. Here, you can see the soft nucleophiles like lithium organocuprates, thiols, all these attack the beta carbon, that is soft nucleophile. They result in 1,4 conjugate addition. These form the 1,4 conjugate addition. Now, coming to the application of the HSAB. Coming to the application of the HSAB, already previously I have discussed it. Yeah, hydrogen bonding we have discussed. Linkage of the ambidentate ligands to the metal we have discussed. Site preference in the organic reactions. Which site to prefer we have discussed. And the next application, that is inorganic reactions, we'll see. HSAB principle, it is used to predict the outcome of some of the reactions. So for example, arsenic fluoride, you take. And here, this arsenic, the following reaction it is possible. Arsenic is softer than phosphorus and iodine is softer than fluorine. Phosphorus iodine. So arsenic fluoride and phosphorus iodine. Here, these two are getting exchanged. So both arsenic and phosphorus are soft, but relatively arsenic is more softer. So arsenic tends to bind with I3 and fluorine tends to bind with the phosphorus. So therefore, the stable compound arsenic iodide and phosphorus trifluoride are formed. Now we'll see one more reaction, magnesium sulfide and barium oxide. In magnesium sulfide barium oxide, so magnesium, there is exchange with respect to oxygen and barium gets exchanged with sulfide. So the following reaction is possible since magnesium is harder acid than barium and oxygen is harder base than sulfide. So therefore this exchange reaction takes place. Coming to the precipitation reactions, softer acids like silver, mercury, Hg plus, Hg+2, etc. and borderline acids like ferrous, nickel ion, copper ion, zinc ion, lead ion, etc. All these get precipitated as sulfides from their aqueous solutions. Since sulfide ion is a softer base, so the softer acids like silver, mercury, and even the borderline acids like iron, nickel, copper, zinc, lead, etc. can be precipitated as sulfides. So sulfur is so friendly, it's so softer, such that the softer, this is a soft base, and therefore the soft acids come down. So we can see the precipitation reactions almost in the second group. Once if you pass H2S in the qualitative analysis, semi-micro analysis, we can see all the first group elements, the second group elements and the fourth group elements, they get precipitated as sulfides. The interaction is soft acid and soft base. Therefore, a stable compound is formed and thereby the precipitation reactions takes place. Yeah, this is already explained to nucleophilic addition of alpha beta unsaturated carbonyl compounds can also be explained. Now, in the nucleophilic addition, we have seen how the attack is taking place. For alpha beta unsaturated carbonyl compounds, the carbonyl carbon is hard nucleophile and beta carbon is a soft electrophilic center. So, at the carbonyl carbon hard nucleophilic center, a hard nucleophile can be attached. And for the soft electrophilic center, soft nucleophile can be attached. There we have the example RMGs can be attached to that carbonyl group and alcohols can be prepared. Similarly, at the beta carbon soft electrophilic center, dialkyl copper lithium can be attached and you can get the 1,4 conjugate addition. Now, relative strengths of hard hydra acids, that is HF, HCl, HBr, hydrogen iodide, all these relative strength of the acids can also be explained using the HSAB principle. In aqueous solution, the relative strength of HF, HCl are predicted. The reaction of the acids is given here. HX plus water gives rise to H3O plus X minus. The hardest base F minus will be most successfully and strongly bonded to the hard acid. So fluoride is the hard base and strong bonding takes place with hard acids, that is H plus. H plus is hard, so all the hard bases combine here. Therefore, HF is highly stable. It is least dissociative. Acidic strength also increases. You will see here HI, HBr, HCl, HF. So the dissociation also is the same. It is having the least dissociation. Now, the relative stability of the complexes in the aqueous solutions. Relative stabilities in the complexes in the aqueous solutions. HSAB entails that cadmium cyanide is more stable than cadmium diammonium cadmium. So according to HSAB principle, hard prefers hard and soft prefers soft. Hence, soft acid is cadmium. This will prefer to coordinate soft base, that is cyanide. Okay. Soft acid is cadmium and this prefers to coordinate with soft base cyanide. It is clear from the K constants where cyano complex has here K is equal to 1.4 to 10 power of minus 19, while the amine complex it is 7.5 into 10 power of minus. So cyano is more stable. Here this value, see minus values, so the K value is more for cyano than the amine complex. Therefore, cyano is more stable. Hard and soft prefers soft. Yeah, hard prefers hard, soft prefers soft. So soft acid cadmium prefers soft cyanide. Cadmium prefers cyanide. But whereas cadmium doesn't prefer ammonia. This ammonia is here. Cadmium is hard, even cyanide is hard. Here cadmium is hard, ammonia is soft. So therefore, this doesn't get bonded properly. So cadmium hard and even the cyanide is hard. This both prefer properly. And similarly, the soft cadmium cannot prefer the hard ammonia. Therefore, the stability is decreasing. Now, to predict the course of the reaction is also possible. You see that H plus ion, methyl mercuric oxide, what it gives? H2O plus methyl mercuric ion. Similarly, H plus ion with methyl mercury sulfur. So this S combines with H. Therefore, stable compound is formed. Hard and hard. Sulfur is hard base, hydrogen is of hard acid. So this prefer to form the stable compounds, which is getting and methyl mercury is formed. So in this reaction 1, it goes right to the hard acid, binds strongly to hard base. Both. And it produces stable product that is water. Produces stable water. Next, on the other hand, the reaction is favored to the F, whereas soft base SF will tend to remain combined with soft acid. Instead of joining with the hard acid, it joins with the soft acid. CHHG is formed. Stability of the complexes can be detected. Pearson explained the stability of the complexes on the basis of the Hs reactions. If acid and base form an acid base complex, A and B both are hard or both are soft, then complex is stable. If A is hard, B is soft, or vice versa, compound is least stable. So, for example, we'll take AgI2 is a stable complex, but Ag is not. AgI2 is stable. Both of them are hard acid and hard base. Sorry, soft acid and soft base. Ag is soft acid, iodine is soft base. Stable complex is formed. AgF2, it is unstable. Silver, Ag is hard, whereas F is soft. So because Ag is the soft acid, iodine is the soft base. So the interaction Ag soft acid with soft base forms stable complex AgI. But fluoride is the hard base. So interaction of the soft acid Ag plus with hard base F minus forms unstable complex Ia. Ag plus 2 I minus gives rise to AgI2. Ag plus cation, Ag plus cation plus 2 iodine soft base. These two combine to give rise to AgI2 minus. Give rise to AgI2. This is a stable complex. Similarly, Ag plus and 2 fluoride ions gives rise to AgF2. Ag plus silver plus is soft acid and 2F minus is hard base. So AgF2 formed is unstable. And similarly, CO plus 3 is hard acid. 6F minus is hard base. They form cobalt hexafluoride complex, a stable complex. Yeah, we can take instance of one more. Cobalt CO plus 3 with 6 iodine. Cobalt is the hard acid and iodine is the soft base. So cobalt hexaiodine is unstable complex. Now, then still you can go further. Still we can go further. Predictions, that is feasibility of the reaction can also be explained. Before giving you one more application I have to discuss, prediction of the feasibility of the reaction. So feasibility of the reaction according to HSAB, the compounds or the complexes would be stable involving soft to soft, hard hard interactions. Compounds formed between hard soft and soft hard interactions are unstable. Lithium iodide plus CS fluoride gives rise to LiF plus CSI. This is a good interaction. LiF is hard hard interaction. CSI is soft soft interaction. Therefore, this is stable. Similarly, H plus ion, methyl mercury oxide. So methyl mercury plus H2O is formed. That is the good interaction, the feasibility of the reaction is feasible. H plus ion with CH3 HGSH gives rise to CH3 Hg plus H2S. If CH3 Hg plus is stable, H2S is also stable. Coming to the H2S hard and this is hard. So therefore, both of them, hard base and hard acids, there is a good interaction from stable complexes. Reaction proceed in the forward directions because hard acid combined with the hard base with water. So reaction B proceeds in the backward reaction. See, the soft acid combines with soft base into form CH3HgSH. So the course of the reaction, feasibility of the reaction are explained. Now coming to the drawbacks. We have many drawbacks. It's almost three to two drawbacks. Explain. Pearson theory is direct contradiction with Fajan rules. And Fajan rules predict the nature of beryllium sounds to be more powerful. But according to HSAB principle, berylliums are and it is expected to show charge control bonding. It results in more ionic nature of the beryllium atoms. But this is not clear. So the explanation is not clear and this is a defect. And similarly, hydrogen ion is hard acid, hydride ion is soft base. According to HSTB, the interaction between them is polar and H2B stable. Still, the H2 is stable. Indeed, H2 is stable molecule, pure power. So even this could be explained. And there are limitations for this theory is without any quantitative scale measurement. He has not given any quantitative scale measurement. HSJD theory considers all the chemical reactions as the acid-base reactions. These reactions can be explained more better when you consider an other point of view. Instead of acid-base, if other point of view is considered, then that would be more advantageous and that would be more better. And the principle is regarded, this is exclusive, approximate conditions are taken. So hard acids may complex with soft bases, soft may complexes with hard, and can form soft stable complexes. So it's an exclusive one, and not always the quantitative scale of measurement is there. So these are the limitations. So I couldn't explain his expression couldn't be satisfied for some of the compounds. So you need H2 stable, but that couldn't be explained by Pearson theory. So these are the drawbacks and limitation for this theory. So in this class, we have discussed about the applications of the HSAB principle. So again, we have recalled, in this class, we have recalled about the HSAB principle, types of the compounds, types of the class of the compounds, and the principle, and in the periodic table where they are, what are the key characters, what is the principle. Applications. So almost 8, almost to 8 to 10 explanations were given, applications were being explained, and drawbacks and limitations are also explained. And the conclusion is hard electrophile tend to react with hard nucleophile. Soft electrophile tend to react with soft nucleophile. Hard interaction is covered primarily by electrostatic interaction between positively charged electrophile and negatively charged nucleophile. Hard interaction governed by electrostatic attraction between positive charged electrophile, negatively charged nucleophile. Soft interaction is covered primarily by mixing overlap of the orbitals between nu of the electrophiles and home of the nucleophiles. So we have seen many examples of the hard soft electrophile nucleophile and the role played by the HSJB during the conjugate addition. HSJB is one of the several factors that determine the outcome of the nucleophilic additions of the alpha beta unsaturated carbon compounds. So these are the final conclusions drawn by the HSJB Pearson. So I hope you have understood this today's class. If any doubts arises, go through again. Okay. Thank you.